So I'll go ahead and start with today's topic. The topic name is Introduction to Torsional System. It's not introduction though, like we'll cover everything here, but that's how it's called. Okay? So at the beginning, I will start with basically asking you some basic questions. So
on the exam, do we get cheat sheets?
yeah, you have to bring with you a cheat sheet.
Okay.
You write all whatever you want, face and back, and don't be like stressed if you forgot anything, like during the exam. If there is like a question that I ask you about something and you forgot to write down the formula in your cheat sheet, I can give it to you. Okay? So don't be stressed. Hopefully you write everything, but if you got anything, like don't be stressed. Like I will give it to you. Okay? So I will start first with asking you some questions. So if I have a beam like this, okay, and I applied bending moment like this. So I'm applying bending moment around x. So I'm pushing around x. So what is this thing gonna bend about? Which axis? So if I'm using those axes, so I'm bending it like this. So what axis so what is the axis that this beam is bending about? X. So if I apply a moment about x, like here, so that's what we call mx. Okay? Same thing, if I applied moment, so my hand, I'm applying moment like as if I'm applying moment about y. So what do you expect this beam bend about? Which axis? So, okay, so the beam should surround the axis of bending. So what axis of bending it's bending about? Y, okay? So now this is the y. The last thing, which is this lecture about, is how if I bend this beam now around z, which is mz here, what do you think it's gonna bend about? Z, right? So it's still bending about what? Which axis? Z, right? So this is what we call torsion. So we have mx, we have my, and then we have mz, which is we bending about the longitudinal axis of the member, and this is what we call torsion. Okay? So for the beam, we have 3 moments. We do have mx, we do have my, and then we do have mz, or we can call torsion, or we can call it torque. Okay? In today's class, we're gonna focus on mz. In the next couple lecture, we're gonna cover mx and my. Okay? So what is the torque? So torque is the moment that tends to twist a member about its longitudinal axis, and it's self-explanatory. And let's do an application here. If I have 2 members like this, okay, and I'm applying on this member, I'm applying at 80 Newton here and 80 Newton up. So let me tell you something. If I took this beam out, and I'm applying here 80, and I'm applying here another 80. Do you think that this beam is stable? And by stable means it cannot move. So this beam, will it move or no? How can we? Okay, that's right. But how can we check this, like in the mechanics of solid point of view? How many equilibrium equations do we have? We have 3. Summation fx, summation fy, summation moment. So summation fx here is useless. Summation fy, it seems to be stable because the force is going to cancel each other. But the last thing, which is summation moment about any point in a beam, should equal to 0. In the first lecture in statics, you usually used to take a moment about, for example, supports to cancel the reactions. But like you can take a moment about any point. So here, for example, if I took a moment about any point in this beam, I will end up with a value. It's not going to be equal to 0, right? So if I took a moment here, I will have 80 times this distance, and there is no any moment that will counter this acting moment. If there is no moment that will counter that acting moment, which usually comes in a form of fixation or anything, that means it's gonna move. That's why this beam gonna rotate clockwise. That's why you all said that this beam is unstable. So the point here, when you have two forces that is equal and opposite in direction, they will form something we call what? Couple. So we can cancel these two forces, and these two forces will apply a bending moment, which is a couple, like the couple will form a bending moment, and that's how we can apply a bending moment at point B. So the free body diagram for this beam that I'm highlighting in red, it's gonna be like this, and you have a fixation, and you have a value of a bending moment here. And anyone can tell me what's that value of that bending moment? That's correct. So someone said 80 times 500, or you can say different thing. Why don't you take a moment about B? So if you took a moment about B, I will have 80 times 300, then, oh, it will be 0 if they will in the same direction. That's when they will cancel each other. But if you took a moment about B, I will have 800 times 300, like this, clockwise, and then I also have 80 times 200, also clockwise. Do you all see this? So I will end up, do you all see that why they're not going to be equal to 0, right? So I will say this 80 times 300, which I'll end up moment this way. And this 80 times 200, I'll end up in a moment the other way. So they don't cancel each other. They add up. So what I would say 800 times 300 plus 800 times 200, which is in different word, if I took 800 as a common, I will end up 300 plus 200. So if I want to get a torque, you can basically take one of these forces and multiply it by the whole distance between these two forces. Yeah, tell me.
Why 800?
My bad. It's 80. Thank you. Thank you. You all agree with me? Any questions so far? So that was like revision of what you did before in statics. Let's now take it a little bit like step further and discuss what's happening when we apply torsion, for example, on this beam. So imagine I have a line like this, which is I drew it here, and I fix one location, and I will bend the other, and bend it about z. And when I say bend it about z, it's a torque, or a torsion, right? So what's happening to this line? Yeah, this line starts from the original axis and start to bend like this, right? And the reason why it returned back to its own position, you all know, because of the modulus, right? Because we are still within the linear elastic range, right? So you all agree with me now. When I apply a torque, this red line will be like this. Okay? So let me take a strip here of a dx and see what's happening here. Okay? Which is I prepared, this is the strip that I want to take. Okay? I want to take this portion out and discuss what's going on in there. And the reason why I want to do this, that I want to find the relation between the shear stress and the radial position rho. So let me explain it further. If I do have this line, and then it's gonna rotate when I apply a bending moment or a torsion like this, right? So what is happening? Originally, I had the beam, when I take a cross section, I had a beam, and I drew the line like this. And when I apply a torsion, and this torsion gonna be something like this, mz or t, it's gonna end up here. This is A star. Let's say that this guy here was A, and this guy up here is A star. And the angle between them, this is what we call phi, which is angle of twist. Okay? pretty basics. I didn't do anything hard until now. So I had a point A, and when I rotate it, it moved to A star, and this is in the cross-section level. When I take a cross-section, I have point A moving to point B, and the angle between them is the angle of twist. In some application, and we're going to derive the equation for this later in this lecture, some application we want to limit how the rotation gonna be. We don't want the angle of twist be, for example, 360 or something like this. An application for this in the car, and we don't want the angle of twist to be more than, for example, one cycle. That's why we are interested in deriving this equation in this lecture. So let me tell you one more thing before we start deriving an equation. We used to have mz here, which is a torque, right? So that's a bending moment, and this bending moment, what is applying on the cross section? So this bending moment is applying a torsion or a torque. So that's like a shear or a normal. So is the moment is parallel to the cross section, or it's perpendicular to the cross section? It's a shear, right? So this moment is parallel. So as if I'm applying friction on the cross section, right? So if I wanna break up this bending moment in the section level, I will have a force here, for example, a small force, which I will call it dF, and dF is a distance rho from the center. So when I apply dF times rho, I will get, for example, the bending moment, which is, I will call it dt. And the reason why I'm adding d here, that's I need to integrate this. In different words, if I do have a lot of these forces in this cross section and I integrated it, that's how I will get the torsion. Okay? So now let me explain something which might be obvious. This force, I will apply by this rho, which is the distance, I will get a torsion, right? So what if I took a force that's a little bit farther from here? So I'm increasing rho, right? When I increase rho, will this get me a higher torsion or a lower torsion? Higher. Which also tells you that the stresses further from the center, that's where I have the higher shear stresses. So let me derive this if you didn't understand what I'm saying. So let's now find the relation between the shear stress and the radial position rho. So I have dF and I have position rho, and if I divide this dF over the area that I'm taking, I will have the tau. Okay? Force over area. Okay, so let me take this guy out, and I'm gonna copy it. Okay. So originally, this was something like this, right? And when I applied torsion, it went like this. Do you agree with me? Okay. What does this remind you of? Or in other words, what was this angle from the previous lectures that we discussed? What's that? That's correct. So this is a shearing stress that's happening here, and then within the shear stress, what was this angle? What we used to call it? Anyone? It's what? That's correct. That's a shear strain. Do you all see it? If we have a plate that's like this, and we didn't apply any tension or compression to that plate, what we did, we just rotated it. And when we rotated it, we move it that way, which is parallel to the cross section, we will end up having a gamma here. Okay? So now I do have a gamma, And let's say this is the cross section. And originally, we used to call this point A, and this is, for example, the A star. And from what we said earlier, from the cross-section level, this angle, what we call this angle, phi, which is the angle of twist. Okay? So what I want to do now is I want to show you something, which is from what you see here. We already agreed on basic stuff. We already agreed that this angle is angle of twist, and what's coming from there is the gamma, which is the shear strain. Okay? So do you see that the gamma from the center is starting from 0, and it starts to increase until the maximum? What is the maximum? Do you see that the maximum happened at the top or at the perimeter of the cylinder? So what I'm interested in here, I want to take this triangle out, okay? And I want to find the relation between the maximum, so this is the gamma. I want to find this distance related to that distance using this triangle. And in a minute, you will understand, everything will make sense. But just bear with me. So from the shear strain, what was this length? If we are given that the angle gamma and this strip is dx, what was this length? Say that again. dt. What's dt? So again, we have this triangle. We used to do this in the shear strain. We have a gamma, and we have a dx. What was this deformation? So do you agree with me? So gamma is equal this over this, right? So this guy will equal to dx times gamma, right or wrong? Some trig here. So if I took this triangle out, this triangle is this one inside. And at the top here, I do have, and I'm going to call it gamma max times dx. And the reason why I'm calling gamma max, because you all agree with me, at the top I have the maximum gamma. But when I go down, the gamma starts to decrease until it's 0. Do you all see this? Okay. And I will take the gamma, again, at any point here in the middle. So this will not going to be gamma max. This is just going to be gamma times dx. Okay? The strip is again dx, but at any point down, any point, I do have a gamma times the dx. One more thing I need to highlight is from the radius, from the center to the preference, what we used to call this line. This line, this is, I have a circle and I have a center. What is this length? This is the radius. Or this is, let me call it rho. Okay? Pretty basic. Are you confused? You sure? Okay. So let me tell you something. You all told me that this is the radius. So at the radius, let me name it, rho is equal to c. Okay? I'll call the whole radius c. But any point, because I want to make this variable, at any point within the radius, I'm going to call it rho. So let me name this as a rho. And at the far point here, I'm going to call it c, because that's when the rho is going to be equal to the whole radius. So at any point, it's going to be rho. At the end, I'm also having a rho, but now at the end, it's constant because the rho is c. But at any point in the middle, I don't know what the value of rho is, so I'm going to name it rho. Okay? So using trig, what I want to find is I want to find the relation between these two lines. So what do you think the relation between these two lines are? So gamma max times dx over what I'm basically doing, I'm taking this over this equal to this small guy over that small guy. Similar triangles, because they share the same angle. So gamma max dx over c is equal to gamma dx over rho. What I can do here, I can cancel the dx together, and I will end up having gamma, let me write in a different color, gamma is equal to rho gamma max over c. So let me break up this equation a little bit. Let me put a bracket here, and let me break up this equation a little bit by saying that G, which is the shear modulus, used to equal, or still equals, shear stress over shear strain, right? We took this before. So now, if I do have a gamma max, I'm going to end up with tau max over G. And if I do have another gamma, which is like, for example, another gamma which is not max, any other gamma, I will end up with a tau that's not max over G. Both of them has the same G because G is constant, but the tau changes when the gamma change. Okay? G is a constant. So when I plug those back in this equation, what I'm going to end up with from this side, I'm going to put tau over G is equal to rho over C times tau max over G. What I'm going to do, I'm going to cancel the G with the G, and I'm going to end up with tau is equal to rho over C times tau max. And this is the equation that I was telling you. This is the relation between a shear stress at any point within the cross-section relative to its radial position. So we all agreed that at the end I do have a tau max, but this is not always the case. Also, in this class we are interested to find a max, but in some application we want to find what is the stress at any point within the cross-section. As long as you know where is that point is, you can divide the distance, which is like where that point is, over c, which is the radius times tau max, which is kind of like a portion of the tau max. So let's say, okay, what if I want to find the stress at rho equals 0, which is at the center? So using this equation, I'm gonna get 0, which tells you that the shear stress at the center is equal to 0, which means that the material that in the middle is useless. That's why we can take this material out and we can use it elsewhere. We can put it at the end. Do you all agree with me? Okay. And this is what we're going to play around in a lecture about the moment of inertia. We need to find where the places that has stresses so that we can optimize the material usage inside our cross-section. I can take the material in the middle out and put it elsewhere. Elsewhere that's useful. In the middle, I don't have stresses. And this concept is going to be of use when we take a lecture called composite section, when we have two materials, a strong and weak. So from this concept, if I have two strong materials, steel and timber, for example, and you want to optimize the use of the cross section, where you will put the steel and where you will put the timber?
Steel on the outside.
And the timber in the middle. Do you all agree with what they said? The reason why is we have maximum stresses outside, so I want to put a strong material. In the middle, I don't have, or I barely have stresses, so I can literally put garbage in the middle, because like anything, just to fill anything. Okay? Okay. Now, if I want to find tau at rho is equal to c, so now look, the equation will turn out to be c over c times tau max, which is tau now will equal to tau max. Okay. Let's now, what we did now, we found an equation or a relation between a tau at any point within the cross section. But we don't see any torsion here, which is the m over mz, right? So now we want to find a relation now between the shear stress and the torsion. And let me start by saying, okay, this is the cross section. Did I lose anyone here, or you understood what I said earlier? Okay. So this is the cross section, and this is the center, right? And I took one of the forces, and let me show you something. I didn't show it to you. This is how the force is going to be distributed. You all see it, right? So I just like here took one of them and multiplied by rho, and that's why I call it dF. But the reason why I'm calling it dF, because you all know from calculus that when I add dF, I want to integrate this. So one force here is called dF, but if I want to take the whole forces, I'm going to take summation of dF. That's when I will get everything. And when I take summation of dF times the rho of each one, that's how I will end up with the mz. So this small df's is just a breakup of the mz. Okay? That's just basic calculus. And when I integrate those, I'm going to end up with mz. So let me take one of them now, one of the df's. And still I do have this rho. And you all know that if I have a force times the perpendicular distance, I'm going to end up with a moment. Okay? So if this force is distributed over area, a very small area here, and when you also have a very small area from calculus, we used to call it dA. Again, a lot of integration here, but like the whole point here is that I want to show you how we derive that equation so that you understand what you are substituting in. Okay? So now I do have dF, and I do have a rho. And if I multiply dF times that rho, I'm going to end up with dt. Okay? From one force, I'm going to end up by one dt. But what will happen, I told you that this dF, when we take a dF, it should be over a very small d area. Given the dF and given the d area, can you get a stress out of this infinitesimal element? So you have a force and you have an area. How can I get stress? Force over area. But now you need to tell me, is this a normal stress or shear stress? Shear. Because the force here is parallel to that area, right? If I did have a dF that's coming in and out, that's when we will have a normal stress. All the stresses share the same thing, force over area, but you need to know what's the output is. So now, if I said dF times d area, dF over d area, I'm going to end up with the shear stress, right? So, which, if I'm just like trying to put it in a nice way, so that dF now is equal to tau d area. This came from here. Okay? So this was a side thing, but don't forget the whole thing that I want to get the dt. And I explained to you, when to get the dt, I want to integrate the whole df's. So now, if I want to get the dt, so I have a dt, and dt is equal to d force times rho, right? And then I'm going to remove this dF, and instead I'm going to put the stress, which is tau times d area. So tau times d area times rho. And again, don't forget, I added the d because I want to do integration. So I'll add an integration here, and I want to integrate this over an area and over an area. And when I integrate all the dt's over that will come in this area, I'm going to get the torsion. And what I want to do now, I want to integrate over the area tau times rho. Just remember, a couple minutes ago, I had the tau is equal to rho over c times the tau max, right? I'm going to take this guy, and I'm going to replace it with the tau. So I'm going to end up with integration area rho over c times tau max times rho d area. Let me put it now in a nice way. Rho tau max over c integration rho square over an area. From statics, when we multiply area times distance square, what was that? It's okay. So it's just a question, because we're going to cover this in the next couple lectures, but I was thinking that some of you might know it. But this mathematical equation, when we multiply the area times the distance square, that's a resistance to a type of a deformation, okay? So let me move to this side. If I do have this cross-section, and I want to find the resistance of this cross-section to bend about x-axis, which we're going to use in the moment. So now, at the beginning, I told you when I apply a moment about about x-axis, this thing going to bend about x-axis, right? X is here. So one of the things that governs how this element going to resist the deformation is the area times the distance square of this cross-section, which was something we call moment of inertia. If you didn't know about it, we're going to explain it in great details in the next couple lectures. But the whole idea of this is that if I have a cross-section and I took like a very small piece and I multiplied this very small piece times the distance from x, which is y, the integration here of this very small area times y, and not only y squared, this is something we used to call moment of inertia. Does that ring a bell? I'm going to explain it. So Ix, which is the resistance to bending about x, we take the area, which is this area, times the distance square. And in the same manner, if I want to find the resistance about y, I want to say integration x square, which is the rotation of this area about the y-axis. Okay, if I found this value is going to tell me how this area or this cross-section going to resist the deformation. So now, Ix and Iy, we're going to use it in the moment equation in the bending stress, which is the next couple lectures. We're going to use Ix and Iy. But now we are interested in z. So if I rotated this element, if I multiplied the area of this element times rho square, which is a resistance to rotation about z, which is now what we call torsion. This is something we call polar moment of inertia, which is, we call it Iz or J, which is integration rho square d area. So what I want you to know now, that the Iz or J, or the polar moment of inertia, that's a resistance to torsion, okay? And this is what we found here in this equation when we integrate. So now I'm going to remove tau is equal tau max over c times j. So now to find the tau max, I will say Tc over j. And that's the relation between the shear stress and the torsion. Is that clear? A lot of integration, a lot of derivation here, but like it's important that you know where everything came from. So now if I ask you, so the reason why I do have a tau max here, anyone can tell me why in this equation I do have a tau max? So I do have a torque, which is a value of the mz. I do have a j. And what is c? C is the radius, right? Which is at rho equals c, which is the radius. And that does make sense to get a tau max. But if I substituted with any value of rho that's not c, will I get a tau max? That's not tau max. That's why when I ask you a question, what is the maximum shear stress due to torsion? So you know that you need now to substitute with this value of C. But what if I draw to you a cross section like this, and I told you what is the value of shear stress at that point. And that point, I'm going to give you a rho is equal to some value. What you should do, instead of using C, you will use that rho. But you should know that you're not going to end up with a tau max. Is that clear? OK. So to get that, let me write the general equation. The rho is equal to the torque times rho over g. And that's the general equation to get the shear stress at any point. Shear stress due to torsion at any radial distance rho. The torque here is the moment about z, which is torque, and it has a value of the bending moment, which is, for example, kilonewton meter. Here, rho is a radial distance, which is going to be in a unit of length, which is meter, inch, feet, and J is the polar moment of inertia. Okay? The polar moment of inertia, though, it does have a table. So in this table, it tells you that the J for a circle is pi d power 4 over 32. And this is also for a ring. We are not interested in this class to find a rectangular or a square section, because they have different equation and different approach. But since you understood what I did to come up with the equation for the circle, you can do it yourself and find the square or rectangle. So in advanced classes, when you want to study the rectangle or square, I'm pretty sure if you follow the same approach, you're going to end up with the same, like with similar equations, okay? And of course, I don't want to show you an equation that you don't know where it come from. I know it's kind of boring, but for me, when I was a student, I wished if someone would explain to me how everything came from, so that, like, to be an engineer, like, I don't want to see equation that I don't know where it come from. So if I will only derive one equation, but if you derive the other equation, you're going to end up with the same thing. So what I want to do, I do have a circle, and I'm going to take a dA here, which is like a small element or a small strip. And when I take a small strip, that means I want to integrate, which means I want to integrate over this whole area. So if I know that this distance is rho, and this small thickness is d rho. Okay? Now I want to find the polar moment of inertia for this whole thing. So as you remember, the polar moment of inertia is integration rho square times the area. So the area here of this ring that I want to integrate the whole section over, I'm just going to take it out. If the area of it's not in your mind, what I want to do, I want to take this guy and I want to put it in the form of a rectangle. Just I want to like elongate it like this. So what I will end up with the length of this is going to be the circumference of that circle. If you know rho, so the circumference of that rho is 2 pi r, which is the radius, right? Or 2 pi rho. Is that clear? And to get the thickness, we already said that this thickness here is d rho. So now this guy, the area of that guy, is a rectangle of 2 pi rho times dp. So integration rho square, and the d area here is 2 pi rho times dp. And I'm integrating from 0, which is at the radius equals 0, to this whole radius. Okay? And this whole radius, let me see what I named it. I named it C, just to be consistent with what we did before. So I'm going to integrate this from 0 to C. So what I'm going to end up with is 2 pi integration from 0 to c rho power 3 dp. You all know when I integrate something, I raise the power by 1 and I divide it by the new power, right? So I will say 2 pi over 4 rho over 4 from 0 to c, which is now pi over 2 c power 4. Is this what we see here? No. No, it's not. Because what I used here is c, which is the radius. But if I want in form of diameter, what I will say pi over 2. And what's the relation between the c, like the radius and the diameter? So I will say d over 2. The whole thing is to the power 4, right? Diameter is equal to 2 times radius, so the radius is diameter over 2. And you will end up with pi over 2 times d power 4 over 16. And 16 times 2 is equal to what? 32 d power 4. So now you understood where this equation came from. Okay? We're not going to derive this, but you can derive it by yourself, and you're going to end up with the same equation. But once you know the approach, I'm pretty confident that you can go it by yourself. So now the last thing, which is going to be a little bit easy because we already covered it before. I'm going to take this guy here to derive the equation for the angle of twist. Last thing we're going to derive today. I promise. So from this cross section, I want to find this arc length. And do you remember from statics, what was the arc length? If I want to find the arc length, which was s, what I would do is I'll multiply pi times the radius, right? So this guy, which is the strip that I took it before, this element here is pi times rho. Or, yeah, here we can call the rho is equal to c. Okay? That's from the cross-section side. But what about from this side? What is this length is equal to? We already said that before. Gamma times dx, right? So we can basically say pi times rho is equal to gamma dx. And again, when you see dx, that means that we want to integrate over the whole length. So pi is equal to gamma over rho dx. So the small portion that we took was dx. What we took this from? We took it from that beam, which has a length of an L, right? So logically, what we want to integrate over, we want to integrate from 0 to the whole L. So now, I'll put integration here from 0 to L. And from 0 to L, I'm gonna have gamma over rho times, because this is a constant, so I'm gonna take those out, 0 to L dx. And what is the integration of nothing? It's x, and then I'll put L in there. Do you all see this? Okay. And that is the angle of twist. But the thing is, I want to tell you something. We're going to take this guy, the gamma, which I'm putting in green here, and I'm saying since gamma is equal to tau over g, right? That's the shear strain equation. And then we just concluded a moment before that the tau is equal to torsion times rho over j. So I'm going to put that here. So T rho over j. What I'm going to end up then, when I substitute this guy in the angle of twist equation, I'm going to end up with angle of twist is equal to, this is T rho over j. So what I'm going to end up with rho, I'm gonna remove the rho. Okay, again, I'm gonna remove the rho and put tau over j, and I'm gonna remove that tau, and I'm gonna go t rho over j. So it's gonna end up with something like this: t rho over j over g, because I'm removing this and I'm putting this, and then I'm putting this whole equation instead of this rho times L over rho. What I see here, I can cancel the rho with each other, so I'm getting the equation which is TL over JG. And that's how we can find the angle of twist. So the angle of twist is function of the torque, which is the moment, the length of the beam, G is shear modulus, and J is the polar moment of inertia. Okay, and that's all the equation that we need to solve the torque problems. Any questions so far? A lot of integrations, a lot of derivations, but it's important for me that you know how everything came from. Okay, I don't know if I have time, but the last thing I can say in this 2 minutes, that now let's start solve the problems. So it's gonna be pretty easy, because when I have a problem like this is how you're gonna see the torque applied. So it's either I'll put the torque in these plates like this, and this plate are gears, or I can just like put the torque like this without any gears. Okay? And now we're gonna use something we call the right hand rule. We can't draw anything with this bending moment. So with this torque. So I wanna be able to draw the free body diagram for this beam. Using your hands, your right hand rule, make your fingers follow the bending moment. So if your fingers follow the bending moment or the torque, your thumb will tell you where is this torque applied. Is it applied inward or towards the fixation? So my thumb pointing outwards, right? So I'm gonna put it like this. So instead of having a torque of 50 kips inch, I'm gonna put like a torque that is applying like this, 50 kip inch, as if I'm converting it to axial force. It's not axial force. It is something we call, it is torque that applying outward. What about that one? My hand, make your fingers follow the arrow. So my thumb is pointing inwards or outwards. And inwards and outwards, we call it toward the shaft or away from the shaft. And the shaft here, the reference for that shaft is that fixation. So am I applying a torque outwards or inwards? Towards or outward the shaft for that guy? Outwards. So you're gonna put it like this. 10 kip. What about the last one? Inwards or outward? Towards the shaft. Again, the last thing, it's easy. Can you draw as if you're drawing the AFD? But instead of calling it AFD now, we're gonna call it internal torque diagram. Similar to what we did before. Can you draw as if you are drawing the AFD for this? Hello again. So I wanna continue from where I stopped this morning, but we stopped here, but I want to revise something. I didn't have time to go, over it or to explain it further, but let me do it now. So we did a derivation to find a relationship between tau max, which is maximum shear stress, and the applied torque, right? And I told you this equation, which what we concluded from this integration, we said this equation is function of c, which is the radius, which is at the further distance from the center of the circle. And I told you, now if you want to find tau, not necessarily be the max, you need, instead of applying with p, you need to apply with rho. But how we came up with this equation? It's a one step. I'm not gonna take long in this. So we said that tau max from the integration, we said that tau max is equal to torque times c, which is the radius, over j. But remember, before we derived this equation, which is a relation between tau, which is a shear, at any point in the cross section, at any radial distance rho in the cross section. So I'm going to use this guy here. So I will say, since tau is equal to rho c over t max, then this t max, tau max, is equal to tau c over rho. I'm just like changing, I'm not just putting this tau max in one side and having the rho c in the other side. So I'm going to end up with tau max is equal to c times tau, which is the shear stress, over the radial distance. And I'm going to apply this tau max here. What I'm going to end up with tau c over rho is equal to Tc over j. What I can do is I can cancel c with c, and then I can end up with tau at any point in the cross section, which is the shear stress, T, which is the torque, times rho over j. And that's how I ended up with this equation that I said in the lecture. Okay? So let's now continue from where I stopped. So from where I stopped, it was this beam, but I didn't make it clear that this moment was, these moments are not in 2D. This moment, you want to look at it as if it's in 3D, as if it's rotating around the shaft. So I should have make your eyes, or I should have trained you on those one first, which is the 3D first, and then I move to the 2D. But I switch. So now let's like train your eyes on those 3D sample. So for example, if I have this beam and I want to draw this shaft here, okay, I will just draw the regions. So this is A, and this is B, and this is C. So I have A, B, C. So I'm going to use my right hand, and I'm going to make my fingers follow the torsion. So here, so my thumb here, when I follow the moment, my thumb is pointing toward the shaft, which is toward the fixation. So I'm going to make it look inside, like this. 2 kilonewton meters. And then the other torsion here, I'll make my fingers follow the 3 kilonewton. As you can see, my thumb is pointing outward the shaft, which means away from the fixation. So I'm going to draw it this way. So that's 3 kilonewton meters. And then that's how we transform the torsion into also torsion, but in a way that we can draw the free body diagram for it. So this is the free body diagram for the torsion. And using this free body diagram, I can draw the internal torque diagram for that guy, which, let's do it real quick here. So internal torque diagram. So I'm going to have 2 in compression, and then minus 2, and then I will have plus 3, which I'm going to end up with 1, positive 1. And let's spend a minute here explaining what this means. This means that any point in the torque, in the shaft here, any point here, it's feeling a torsion of 1 pointing outwards. And in a moment now, I'll explain what does it mean pointing outwards and inward. And at any point in this beam, I have a torque that's pointing inwards or towards the shaft or towards the fixation. Okay? So let's do an example here. This example, we have it in the booklet. And what I do have here, I do have already the torsion, but it's already transformed in a form of like axial force. It's not an axial force, but like it's a transformed torsion in expression of away or toward the shaft. So they did the job for us. That's not always the case that they do the job for us, but they saved us a step. So if I have this type of question, so I can start solving it by drawing the internal force diagram. So I will say IFD here. And I'm going to start from the free end. So I'm going to have 10 kept foot tension here. And then I have my calculator. Then I will say plus 10. And then I say minus 25. Because 25 here is opposite to 10. So I'll say minus 25. So I end up with negative 15. Okay? I'll go constant until I see the 5. And then I will say plus 5. So the equation here is plus 10 minus 25 plus 5. So this is plus, this is minus. And I will end up with negative 10. Okay? Now I drew the internal torque diagram. So also the question here continues by asking us, find the maximum shear stress in segment 2, given the diameter of segment 2 is 2 inches. So now remember, it asks us explicitly get the maximum shear stress. So I have an equation for the maximum shear stress is equal to torque at segment 2, maximum shear stress at segment 2, times C, which is the radius at 2, okay, over J, which is the polar moment of inertia at 2. So now, the T here, this is the internal torque at segment 2, and I want to read this value from the diagram. So I have this is segment 1, segment 2, I have segment 3. So segment 2 has a torque of negative 15, and don't forget the negative. So I will say minus 15 kept foot times the radius, and I've given the diameter of 12 inches. So the radius here is going to be 6 inches. But now I see that 15 kept foot and I see inches, so I want to multiply here by 12, so I have a moment or a torque of kept inches. So I'll multiply the 15 by 12, okay? And then the J, which is pi over 32 times the diameter, and the diameter is 12 to the power 4. Okay? If I plug that in, I'm going to get negative 0.53 KSI. And this is the maximum shear stress, and it's so since I have negative, so negative means it's pointing towards the shaft or towards the fixation. So that's what negative mean. So how can I express this in my answer? So you can say, you have two options. You can say inward, which is toward the shaft, or you can make a double-headed arrow pointing towards the fixation, which also tell me that's inwards. Okay? Last thing, it tells us find the angle of twist of segment 2, and the length is given of 10 foot and the shear modulus of 4 times 10 power 3. So I will apply with angle of twist TL over JG. So that's for segment 2, 2, 2, 2, an angle of twist of 2. So the torque at member 2 is still 15 kept foot multiplied by 12 to convert it to kept inches. And then the length is in 10 foot. I'll multiply also by 12 to get it in inches. And J, which is the polar moment of inertia, I already mentioned it before, which is pi over 32, 12 power 4. And the units here is inch power 4, multiplied by G, which is 4 times 10 power 3 KSI. And KSI here is kips over inch square. So my units here will cancel each other. And if all the units cancel, that means I have a radian. And this is the angle of twist that I'm looking for here. So I'm going to get negative 0.00265 radian. And again, you can use the same thing. I can use inward or the double-headed arrow. So I'm going to copy this guy here. And this is how we can express the stress and the angle of twist. Okay. Now, when we have a question like this, we don't have a fixation side, right? And the basis I explained earlier that the stresses and the angle of twist are either towards the shaft or away from the shaft. But now, since I don't have any don't have any fixation, so I'm gonna relate inwards or outward towards one of the ends. So let me explain that. Let me first, also as a practice, let me draw the FBD for this guy, the free body diagram, and I do have the first 80 Newton would be pointing outside, which is the right-hand rule. I'll have 80 Newton meter. And then the second one, my thumb will be pointing inside, 150 Newton meter. And the third one, outside or to the left. Again, there is no inside and outside here because we don't have any fixation, but I will tell you now how can we represent it. And the last one will be pointing to the left, a value of 10 Newton. So that's the FBD here. So if I want to draw the internal torque diagram, I'm gonna have, you can either start from the right or the left, you're gonna get the same answer, okay? So 80 in tension, and then in your calculator you can start with plus 80 because it's in tension, and anything that goes with 80 you can say plus in the calculator. Anything goes to opposite to 80 you can write it negative in your calculator. So I have plus 80 minus 150, I'm ending up with negative 70, and I'll move constant, and then I have plus 60. I'm continuing the equation, so 80 minus 150 plus 60. I have negative 10, and then constant. And as a sanity check, I shown it when I start from the either right or the left. Here I started from the left, so when I started summation from the left to the right, I end up with negative 10, which agrees with this guy, so they will close here at 0. So minus 10 from the left, and I do have a 10 from the right, so that's why they close at 0. I will be wrong if I end up with negative 20 here. So if I'm starting from left to side and I have negative 20 here, and the diagram I have a value of 10 here, that means I have an error of 10. So I need to go back and see where my mistake was, okay? So now when I ask you about the rotation or the angle of twist, I can tell you, for example, if I want to find A, I can tell you find me the angle of twist of A because I don't have any free end, so I need to relate A to some point. And this is also, we already said that before when we spoke about delta. So now I will say, find me the angle of twist of A relative to D. So now it will be inward or outwards relative to D. So as if I'm imagining that D is fixation, okay? So the equation here, so I'm asking you, find me the rotation at A relative to D. So if I want to find the rotation at A, I want you to find the angle of twist of all the segments here, okay? In the previous question, I explicitly asked you what is the rotation or angle of twist of segment 2. So that's when you will use the segment 2. But when I ask you about a point, for example, you need to sum everything. The reason why is in here in the next slide. So in the next slide, I prepared something which I do have a shaft, and before applying a torsion, I draw this green line, right? And after applying a torsion, I had this red line, which is what we explained this morning in the lecture. When I rotate an element, the element, this green line, will go to the red line, right? And at each segment here, I took a cross section. So I ended up having these 3 circles, which represent the sections in this beam. So at the beginning, for all 3 sections, without applying any torsion or anything, I do have this line. I didn't have any rotation or anything. So this was the original line for all 3 of them. So when I rotate this beam or this shaft, so at segment A, as you can see, the red line goes to B. So this dotted line, this is dotted blue line, now rotated to B, which left me with this angle of twist, which I'm gonna call phi1. Okay? Okay, now what's happening in the second segment is I do have, it went to C, right? From what I see here, it went to C, right? What segment 1 calculates here, segment 1 calculates the phi1. If you solve for segment 2 will get you this phi2, which is for this portion, which is, for example, this portion here, because this rotation was already calculated from the first segment, which is this guy. This guy was already calculated from the first segment. From the second segment, you are only calculating this part, which is this guy. So now, if I want to find the total rotation that happens for these two segments, which is this whole thing, you want to calculate phi1 and phi2. Phi1, you got it from the first segment, which is this guy. Phi2, you got it from the second segment. To get this whole total rotation, you need to add 1 to 2. Okay? Same thing with 3. So if you solve for segment 3, like the phi3 here, for this segment, what you're gonna get is this angle. Is this angle only. But is this the total rotation that happened? No, this is not the total rotation that happened. The total rotation that happened is this guy plus that guy plus that guy. Okay, which is phi1 plus phi2 plus phi3. So if I want to draw here, this is phi1 from segment 1, and now this is phi2 from segment 2, and now the last segment is this phi. So if I ask you a question, what is the total rotation that happened at this section? You need to add the summation of segment 1, segment 2, segment 3. Okay? Going back here, if I told you now what is the phi angle of twist of A relative to D, you need to sum the whole 3 segments. And you need to keep in mind that you need to put the signs of the torque. So I'm having 3 terms here, each term representing one segment of the 3. So I will have TL over JG, 1, 1, 1, 1, T2, L2, J2, G2, and for the third, okay? And now when I substitute for the, let me name those segments. So this is segment 1, this is segment 2, this is segment 3. For segment 1, I'm gonna substitute with positive 80 as T1. For T2, I'm gonna substitute with negative 70. For T3, I'm gonna substitute with negative 10, okay? And whatever sign that I'm gonna get, if I got a positive sign, that means I'm rotating, if I got positive, I'm rotating away from D. Again, the reference now here is D. If I got negative, that means I'm rotating inwards or towards D. And so let me write it here. So if I got positive, that means I'm rotating this way. So I'm twisting away from D. So you can write it like this, the 2 double arrow pointing away from D, or you can write it down like it's twisting outwards from shaft or D. And if you got negative, that means towards, which is the 2 double arrows pointing toward D, or you can say, write it down, inwards toward the shaft, which is between parentheses D. Okay, here's the reference. And again, if I did have fixation at D, I will not ask you what is the rotation of A relative to his B. I should say D. So if D is fixed, now I will ask you what is the rotation of A. Okay? I'll not say relative or anything because by default I'm rotating relative to the D because D is the fixation point where it's not allowed to twist. Okay? So, and you will use the same equation here, the whole tree thing. Nothing gonna change. It's just like the naming thing. Last thing, which is I want to explain a little bit further, what do we mean by outwards or inwards? So now, for example, so this was the shaft at A, right? Which is we're still in this example. We're still in this example. So if I got an angle of twist, for example, phi is positive. Or let me not say positive, let me say it away, which is, for example, double arrow away from D. So A relative to D, so away from D. What does that mean? That means that the torque that happened caused the angle of twist to be away from D. So remember, we had, if we want to now reverse what we had before, so before in the question, we had a torque in this form, in this like arrow form, and then I had my finger follow the arrow and my thumb pointing towards whether inward or outward, and that's how we draw this. Now, if I gave you this, can you transform it to this form or no? So now it's easy. So now my thumb will be pointing outside, so the arrow, I will put it this way, which is this side. Okay? Which tells you that, for example, this beam gonna twist counterclockwise. So what can we benefit from this? We benefit from this is if I have, before applying torsion, I have point A was pointing like this, and I'm gonna ask you, for example, what is the displacement of point A? So you know that A gonna move counterclockwise, and by an angle of twist, which is you already solved, okay, and you already have a radius, can you now find me this deformation? Yeah, you will simply say this is an arc length. You will say r times theta. So that's when we will, if we ended up with a theta, or the angle of twist, not theta, phi, pointing outwards. And if we have it point inwards, and instead of having displacement going this way, I'm gonna have a displacement going the other way. Okay? And that's all for this lecture, and I'll see you guys tomorrow. Thank you.